For many engineers deploying large language models, the architecture is treated as a black box. You feed tokens in, and probabilities come out. Inside that box, the standard attention recipe is universally written as the softmax of Q times K transpose over the square root of D, multiplied by V. Treating this equation as a rigid programming snippet hides the actual mechanics of what the model is doing to the data. In 2026, Michel Fabrice Serret published a paper translating this standard NLP recipe back into the strict language of applied mathematics. He reframed attention entirely around linear spaces, kernels, and low-rank factorizations. This formal mathematical primitive provides the analytical framework for deconstructing modern efficient architectures, from grouped query attention to the compressed latence of DeepSeek's multi-headed latent attention. This equation shows the true, generalized form of attention. We start by striking out softmax entirely. The operation is actually y equals z inverse AV. Understanding attention as this generalized operator, rather than a fixed code snippet, provides the mathematical levers required to solve the massive memory bottlenecks crippling AI deployment today. The data flow begins with three simple linear projections of the input embeddings: queries, keys, and values. The queries and keys feed into a generic similarity function, a kernel, denoted by kappa. This generates a raw, unnormalized score matrix, A. In this framework, the z-inverse term isolates the normalization step from the similarity function. Softmax is a specific instance, a scaled exponential kernel plugged into this z-inverse skeleton. Any non-negative kernel fits here. Z-inverse row-normalizes those raw scores into a true probability distribution. Because the rows sum to 1, the final output matrix is a convex combination of the value rows. This brings us to the square root of dqk scale factor seen in the standard softmax recipe. It prompts a specific question: why divide by that exact number? If vectors v and w have independent entries with variance 1, their inner product variance is exactly dqk. Dividing by the square root of dqk forcibly locks the variance at 1. Without it, variance scales with dimension size, saturating softmax and halting training. The magic numbers typically hard-coded into machine learning frameworks are strict mathematical requirements engineered to maintain statistical stability across deep neural networks. A single attention head is a smoothing operator. To increase explosivity, the architecture expands horizontally into n parallel heads, each possessing its own distinct projection weights for queries, keys, and values. This parallel structure allows the model to detect distinct relations in different subspaces simultaneously, like syntax in one head and coreference in another. Their outputs are concatenated and mixed linearly via a trained output projection matrix. For autoregressive generation, where tokens are produced one by one, a strict constraint is required. A causal mask prevents queries from accessing future keys, restricting each query strictly to positions at or before its own index. Applying the causal mask first means adding negative infinity to the scores in the upper right triangle before the kernel. The second method multiplies the output by 0 after the kernel. Both operations yield the exact same z-inverse AV result, being mathematically identical. The causal mask is the formal structural constraint that enforces sequential sequence prediction without leaking future data. Autoregressive generation carries an exponential penalty. Recomputing every token's keys and values at every single decoding step balloons the time complexity to O of n cubed. The industry solution is the KV cache. By storing past tokens in VRAM, the model only computes the keys and values for the newest token, dropping the time complexity to O of n squared. This cache formula reveals extreme memory costs: 2 times layers times heads times cache tokens times head dimension. The causal mask makes caching valid, keeping past outputs perfectly fixed. Grouped query attention shrinks the n heads parameter by sharing KV heads, proportionally reducing cache size. Grouped query attention does not alter the core arithmetic shape of attention. 8 times fewer KV heads means exactly 8 times less cache. It is a pure counting trick required to keep massive language models viable in GPU memory. The memory savings from grouped query attention reach a limit. For next-generation models like DeepSeek v2, that limit is a hard hardware boundary. DeepSeek utilizes multi-headed latent attention, compressing massive per-head keys and values into a single shared low-rank latent vector per token, L. Algebraically expanding the query key dot product reveals a crucial weight merge. Sequence-independent inner matrices collapse into a single head constant block, WLQK, computed once. The second merge operates similarly on the value side. The value weights fold directly into the output projection, yielding a new absorbed matrix, WLO. The operational result is extreme efficiency. The model computes attention scores directly from the compressed latent. The individual K and V heads are never materialized in memory. While the initial projection into a latent space is a low-rank compression, the subsequent attention calculation is an exact algebraic factorization. It replaces the memory bottleneck with a series of precise mathematical substitutions. There is one critical caveat to that exact factorization. The flawless MLA weight merge requires the absence of positional embeddings. Rotary position embeddings, or ROPE, are the industry standard for injecting token position data into a model. They operate after the keys have been constructed. ROPE applies a position-dependent rotation matrix, creating an interaction term that forces its way between the merged matrices. This creates a structural break. Because the rotation term depends on the exact query key position pair, it varies constantly and cannot be absorbed into the sequence-independent constant WLQK. This forces DeepSeek into a compromise. Because pure MLA is broken by ROPE, they append a small non-latent positional vector to K and Q outside the main compression loop. DeepSeek's complex design is a forced mathematical compromise to maintain the latent speedup, perfectly predicted by the structural limits of the rotation matrix. We can ground this abstract algebra in the concrete hardware realities by comparing the cache constraints of Llama 3 70B with DeepSeek v2. DeepSeek's 512 latent dimension is actually wider than Llama's 128 head dimension, but the multiplier effect decides the hardware footprint. MLA caches 1 latent per token. Llama must cache n heads of key value pairs per token. DeepSeek's net memory consumption is drastically lower. The entire efficient attention zoo relies on this sequence of logic. You isolate the Z-inverse normalized kernel, you prove causal caching is valid, and exploit algebraic factorizations like grouped query and multi-headed latent attention. The kernel-first perspective reveals the structural relationship between the basic Z-inverse AV operator and these high-performance variants. Realizing these hardware gains requires a first principles mastery of the underlying linear algebra.